Hello everyone, my name is Harikishore. I'm a graduate student at University of California, Irvine. Today I will be presenting LiftChain, which is a multi-stage transaction protocol for scaling NFT transactions to address some of the scalability issues in the current solutions in NFT marketplaces. This is a joint work along with Sai Vineet, Abhishek Singh and Faisal Nawab from University of California, Irvine, and Ahmed Shoel from Taiba University, along with Sam Agassas from University of California, Santa Cruz. Before jumping into the details of LiftChain, let's look at some of the current NFT market trends. We see that NFT has reached a 40 billion market in 2021, and majority of NFT transactions are of low value below $200, and it takes $100 on average to mint and sell an NFT. Apart from this, on average, it can take any time between a couple of seconds to several hours to process an NFT transaction, depending on the gas price we are willing to pay and the network traffic that we have on the blockchain network. Coming to the main use case of LiftChain, we see microtransactions as the best use case that LiftChain can be adopted for. With the huge popularity and recent surge in NFT market, the existing scalability solutions are not viable for real-time applications like gaming that integrates with the NFT marketplaces. This is especially true for high volume, high throughput applications, and existing marketplaces do have support for fast off-chain transactions with atomic exchange protocols, but do not completely solve for NFT fluidity, where multiple consecutive transactions can happen within a short period of time. Another aspect about scalability is reducing the gas fee of transactions. High gas fees is one of the hindrances in NFT adoption. Finally, we need a transaction processing system that can be easily pluggable with the blockchain and NFT marketplaces. Well, there are several existing scalability solutions. Some layer 2 solutions are Lightning Network, rollups, and state channels. We also have Polygon, which is based on Plasma chain. These solutions significantly increase the transaction speed and throughput. Then how is our solution different from these existing ones? The main idea is that LiftChain addresses the scalability problem at the application level while integrating with a blockchain directly, or it can be plugged with existing layer 2 solutions. Coming to the system overview, LiftChain is a multi-stage NFT transaction protocol that can scale well for high volume NFT transactions, at the same time inheriting the security guarantees of the mainnet. Our model proposes an off-chain marketplace where transactions initially occur with low latency, and the final stage of our multi-stage model interacts with the on-chain to make the off-chain marketplace eventually consistent with the correct state. The current implementation of LiftChain has a transaction processing system in off-chain, and it uses a prototype smart contract based on ERC-721 on on-chain. It provides the capability of performing transactions at near off-chain level performance at the application side. But how can we have near off-chain level performance and at the same time have strong security guarantees inherited from the mainnet? The catch is that LiftChain protocol is only applicable for applications that are tolerable to temporary inconsistencies. LiftChain is best suited for NFTs that do not mutate the state of external application relying on them. Suppose a digital real estate based application uses some blocks of land as NFTs, which can be used for construction. A momentary inconsistency in NFT ownership could lead to irreversible state changes in the integrated application. LiftChain is not suitable in such applications. However, in our security model, we argue that majority of such inconsistencies happen due to malicious sellers, and we show that the seller has little to no incentives to perform such attacks, compromising the application security. Multi-stage invariant confluence with apologies, or MSIA for short, is the main algorithm used in LiftChain for its safety, and it sits at the heart of our protocol. Now we look at a brief overview of workflow of MSIA in LiftChain. First, the client requests an NFT transaction. This is processed by an off-chain node. Every transaction is then broken down into initial and final sections. In the initial section, we check the ownership and then obtain the lock on NFT data item to update its ownership in the off-chain data store and then release the lock immediately. Next, in the final section, we check the ownership again, as by the time the final section starts, the state could have changed. The main purpose of this check is to prevent any avoidable failing transactions, as failing transactions also incur gas fee on-chain. Next, we batch the transaction and run the batch on-chain. Finally, if the transaction fails, we send an apology to the client and update the latest NFT ownership in the off-chain data store. This step is important to guarantee safety of MSIA and LiftChain. Now I hand over the presentation to my colleague Sai Vineet, who will be discussing about safety and security of LiftChain along with its evaluation and future work. Thank you.
Hello all, my name is Sai Vineet. I am a graduate student at University of California, Irvine. Now let's look at safety in LiftChain. In addition to conflicting transactions being serialized in the same order in each section, we also need the property where the final section of the transaction executes after its initial section. We also have to account for transactions happening between any transaction's initial and final sections. The following measures are taken to ensure safety in LiftChain. One is locking. The second one is maintaining invariants, where two clients cannot hold the same NFT at the same time, and also NFT uniqueness. We show that a transaction retracting its initial section is sufficient to ensure consistency and preserve invariants in NFT. We also need to prove that the execution function of MSIA minimizes the number of retractable transactions in off-chain. Coming to security in LiftChain, a malicious attack can happen from a seller who is trying to transfer an NFT without ownership or trying to double sell an NFT. To handle this case, some cryptocurrency can be withheld from the sellers during the transactions to prevent such double selling attacks. Due to failing on-chain transaction also costing gas fee, the attacker has no incentive in trying to double sell. Similarly, a malicious buyer can be thwarted by locking prize funds in the exchange smart contract before initiating the NFT transfer. The application implementing LiftChain can also ensure that the transaction happens in an atomic way. Now let's jump into LiftChain evaluation. One of our main evaluations is comparing the response times of our MSIA based approach with a simple MSSR. MSSR is an implementation of a two-phase locking protocol which mimics the way transactions are held in existing marketplaces. In MSSR, a transaction lock is held until the end of the transaction, unlike MSIA where we immediately release the lock after the initial section is completed, thus reducing blocking. As we can see in this figure, initial section time in LiftChain remains fairly low, whereas its final section and both MSSR's initial and final section times keep increasing with the number of conflicting NFT transactions. As applications are majorly concerned with initial section response times, MSIA based approach is more suitable for scalability. Next, we see detailed initial section response times with increase in the number of transactions. As is seen in this table, the 95th percentile times are around 40 milliseconds, which is pretty close to baseline off-chain performance. The small difference can be attributed to maintaining the data structures and queuing required to process the final section. Also, as seen in this figure, the gas fee varies significantly throughout the day. By spreading low-value transactions using batching during the times when the gas fee is low, showed us a 5-fold improvement in saving. Now, coming to the future work, apart from layer 2 integration, we also plan to build a LiftChain based decentralized exchange to minimize the number of on-chain transactions required for asset exchanges. Machine learning techniques can be used in batching for improvising gas fee savings and for dynamic batch sizes. Finally, we plan to improve our protocol resilience by supporting untrusted off-chain nodes using a permission blockchain system Thank you.